Good afternoon, students. Welcome back once again to the mathematics class. So, in today's lecture, we are going to study some more problems based on first order and first degree of a differential equation. That is nothing but particular solutions. Let's see the examples one by one. First example is find the particular solution of a following differential equation. It is x plus 1 dy by dx, which is equals to 2 to the power of minus y minus 1, such that y equals to 0 when x equals to 0, right? It has been asked in CBSE 2012 also this question. It is CBSE 2012. This question has been asked. So let's see the solution for this particular differential equation. This given equation it is x plus 1 dy by dx, which is equals to 2e to the power of minus y minus 1, right? Now just we have to do here variable separable in the first step. What we have to do, just separate the variables, left one x term one side and y term other side. So what we get here after separating, dy upon dy keep as it is only, this y term take to the LHS, then what we get, 2e to the power of minus y minus 1, which is equals to dx upon x plus 1, right? So now e to the power take to the numerator, what we get here, or multiplying by e to the power of y, what we get, let's see, e to the power of y in the numerator, in the denominator what we get, 2 minus e to the power of y, right, into dy again, which is equals to dx upon x plus 1, right? Just multiplying here e to the power of y, so we get e to the power of y upon 2 minus e to the power of y in the denominator, right? Now integrating what we get, let's say, integration of e to the power of y 2 minus e to the power of y into dy, which is equals to integration of 1 upon x plus 1 dx, right? So now just we are multiplying a minus sign to convert it in the standard form, multiplying minus sign here, e to the power of minus y upon 2 minus e to the power of y into dy, it is 1 upon x plus 1 dx as it is, right? So now which is in the standard form, f of x upon f dash of x standard form, right? So directly what we can do here, simply we can write minus as it is, this term is 2 minus e to the power of I is there, so 2 is a constant term, it is 0, minus e to the power of y is again minus e to the power of y, right? So what we get here, log of 2 minus e to the power of y, that is integration of this term is 2 minus e to the power of y, which is equals to again here also 1 by x form, log of x plus 1 plus of log c, right? Plus of log c. So now we can write it as, which is equals to log of 1 upon 2 minus e to the power of y. Log of 1 of 2 to the power of minus is there, minus taking to the its power means it becomes 2 minus e to the power of minus y, so which can be written as 1 upon 2 minus e to the power of y inverse, so which is equals to log m plus 1 can be written as log mn, so we can write it as log of c into x plus 1, right? So again, which implies log get cancel, 1 minus e to the power of y, which is equals to c into x plus 1, take it as equation 1, right? Now when x equals to 0, y is equals to 0, right? So we can substitute here 1 upon 2 to the power of 2 minus e to the power of 0, that is y value is 0, which is equals to c into 0 plus 1, x value is also here 0, right? So which implies c equals to what? 1 upon 2 minus 1 e to the power of 0 is 1 right here. Therefore c equals to 1 by 1 is nothing but 1 only. The value of c is 1 only. So now put this in equation 1. I'll write here. Put in equation 1, right? Value of c equals to 1. Just substitute the value here. What we get? 1 upon 2 minus e to the power of y, which is equals to 1 into x plus 1. Again, which can be written as, which is implies x plus 1 into 2 minus e to the power of y, which is equals to 1, is our required solution, right? X plus 1 into 2 minus e to the power of y equals to 1 is nothing but our required solution of a given differential equation, right? So next we will see one more example. This example 2. In the particular solution, just we have to substitute the given conditions, right? The initial points, coordinate points they are giving here, just we have to substitute and find the value of c and substitute in that equation, so we get that particular solution. But particular solution already we discussed in the earlier classes. Particular means we have to find the arbitrary constant values, right? Next, see one more example. Solve the differential equation. Solve the differential equation 1 plus y square into 1 plus log x dx plus x into dy, which is equals to 0, right? It has been asked in CBSE 2011, CBSE in 2011, and Punjab Board, it is PB 2009, it has been asked, right? So let's see the solution for this differential equation. The given equation we can write once again. The solution part, it is 1 plus y square into 1 plus log x into dx plus x into dy, which is equals to 0, right? So now in the first step we have to do the variable separable. Just separate the x term one side and the y term other side. So after variable separable, what we get here, 1 plus log x by x into dx, which is equals to, or you can take plus as it is, dy upon 1 plus y square, which is equals to 0. Can we write like this? Just we have separated the here variables, right? X term one side, y term other side, right? Now simply integrate this. What we get? Let's see. Integration of 1 plus log x upon x dx plus integration of 1 plus y square into dy, which is equals to 0. It is constant term. 0 is nothing but c here, right? So, which implies integration of, you write separately, 1 by x dx plus log x, right, and as it is integrating here in the next step, 1 by x dx plus log x into 1 by x dx. Just we are separating 1 plus log x. This is as it is, integration of 1 plus y square dy, which is equals to 0, right? So now, which is equals to, now integrate this, what we get? Integration of 1 by x is log x, right? So that is log mod x plus d by dx of log x is 1 by x, as we know. Now which can be written as 1 by 2 log x whole square, right? Plus 1 by 2 log x whole square plus of, this term can be written as tan inverse of y, which is equals to c. Take it as equation 1, right? So we have written directly at the value. What we get here? Log x 1 by x. The differentiation of log x is what? Sorry, integration of log x is 1 by x here, right? We'll write here, because d by dx of log x is 1 by x, right? So now when x equals to 1 and y equals to 1, when x equals to 1 and y equals to 1, right? It is given values. When x equals to 1 and y equals to also 1, then what we get here? Log of 1 plus 1 by 2 log 1 whole square plus of tan inverse 1, which is equals to c, constant term, right? So which is equals to log value of 1 is 0, it is, plus 1 by 2 into 0 square plus tan inverse 1 is pi by 4, which is equals to c. Therefore finally what we get? Value of c is pi by 4. Put in 1, equation 1, what we get? Log x plus 1 by 2 log x whole square plus tan inverse y, which is equals to value of c is pi by 4, which is nothing but our required solution of a given differential equation, right? Similarly, if you see next example, as we differentiate or we use the method in the general solution, similarly in the particular solution you have to find the value of c and substitute in that, right? That is the difference between general solution as well as particular solution, right? Next, one more example is there. Example number 3. For the differential equation x into y dy by dx, which is equals to x plus 2 y plus 2. Find the solution of a curve passing through the point passing through the point 1 comma minus 1, right? So let's see solution for this one. It is an CRT question, right? So let us consider the given once again here. It is xy dy by dx, which is equals to x plus of 2 y plus of 2, right? So now we are variable separable. First step is variable separable. That is nothing but y by y plus 2, right, into dy, which is equals to x plus 2 as it is divided by x into dx, right? It is variable separable. Now integration of y upon y plus 2 dy, integration of x plus 2 upon x dx. So the next step what we can do here, just we are adding in the first term, just we are adding plus 2 and minus 2. It is y plus 2 minus 2 by y plus 2 into dy, which is equals to integration of this term can be written as 1 plus 2 by x, right? Can we write like this into dx plus a constant term. We will see in the next step, right? This constant c. Now see, which is equals to integration of 1 y plus 2 by y plus 2 is 1 into dy minus 2 keep outside, inside what we get, integration of 1 upon y plus 2 dy, which is equals to here also 1 dx plus 2 outside 1 by x dx, right? So now integrate here, which is implies 1 with respect to dy is y minus 2 as it is log of y plus 2, which is equals to x plus of 2 log x plus of c. Take it as equation 1. Now the points has been given, curve points. Solution of the curve passing through the point that is 1 comma minus 1, which is required family of a curve, right? Which is required family of curve. The required curve passes through the required curve passes through 1 comma minus 1, right? So just substitute in equation 1, x equals to 1, y equals to minus 1. So it becomes minus 1 minus 2 log of 1, which is equals to 1 plus 2 log 1 plus of c. So again, which implies minus 1 minus 2 into 0, which is equals to 1 plus 2 into 0 plus of c, because log mod 1 which is equals to log 1 which is equals to 0, right? So again, which implies minus 1 equals to 1 plus of C. Therefore finally what we get here, C equals to minus 2 is our required value of C, right? So simply substitute this value C in equation 1. What we get, it is put in equation 1, so which is implies y minus 2 times of log y plus of 2, which is equals to x plus 2 times of log x minus 2, right? So simply, which implies y minus x plus 2, y as it is, this x term take on LHS and minus 2 also take on LHS, it becomes plus 2. So here log term we are writing here log of x square into y plus 2 whole square, because if you take this term to this RHS means it becomes 2 log x plus of 2 log y plus 2, right? So log m plus n can be written as log mn, and 2 is the constant term, we are taking its power. Therefore, it is our final required solution of curve. It's nothing but our solution of curve, right? So we'll see next one more example. Next example, that is the volume of a sphere the volume of a balloon spherical balloon is being inflated at a constant rate at a constant rate if initially its radius if initially its radius is 3 units and after 3 seconds it is 6 unit. It is 6 unit. Find the radius of balloon after t seconds. Right? Let's see the solution. What is the question itself? Let's see once. The volume of a spherical balloon is being inflated at a constant rate if its initially its radius is 3 units and after 3 seconds its radius is 6 units. Find radius of a balloon after t seconds, they are asking. So let us consider the solution. Let r be the radius. Let us consider here. Let r be the radius of spherical balloon after time t, right? Just by taking r be the radius of a spherical balloon after time t. So the volume of a sphere is nothing but v equals to 4 by 3 by r cube, right? Next, by the definition, dv by dk, it is dv by value with respect to t, which is equals to k, that is constant, right? Value of sphere with respect to time t we are taking here. So now, which implies d by dt of value of v, just you substitute here, 4 by 3 pi r cube, which is equals to k, right? So again, which implies 4 by 3 pi as it is, r cube can be written as 3r square into dr by dt, right? Which is equals to k as it is. Now again, which implies 4 pi r square, 3 get cancelled here, right? 4 pi r square into dr, which is equals to k into dt, right? So it is a variable separable now. Just we have separated 4 pi r square into dr, which is equals to k into dt. Now integrating this term, let's see, 4 pi outside the integration, inside r square into dr, which is equals to k constant outside, 1 into dt, right? So after integrating, what we get here, 4 pi r cube by 3, which is equals to k times of t plus of c, take it as equation 1, where t initially equals to 0 and r equals to what? 3 here. So just substitute the value here. What we get? The equation 1, when t equals to 0, r is 3. It is 4 pi by 3. It is 27. 3 cube is 27, which is equals to 0 plus c. So which implies c equals to 36 pi when t equals to 0, r equals to 3. And again when the next term, when t equals to 3, r equals to 6, right? So now again substituting equation 1, which implies 4 pi by 3 as it is 260, 6 cube, which is equals to 3k plus of c, which implies 288 pi after dividing, which is equals to 3k plus of 36 pi, which is equals to 288 pi, which is equals to 3k 36 pi, right? So the next step, we can write it as 3k, which is equals to 252 pi, right? Just take 36 pi to the LHS and subtract, we get 3k equals to 252k, which implies finally k equals to 84 pi. K equals to 84 pi. Putting in equation 1 now, that is nothing but 4 pi by 3 r cube, which is equals to 84 pi t plus of 36 pi, which implies 4 by 3 r cube, which is equals to 84t plus of 36. By taking pi common, we get cancel here. So r equals to finally 3 times of 21t plus 9 to the power 1 by 3, right? Can we write like this? So finally we can write it also 970 plus 3 to the power 1 by 3, which is our required radius after t second, which is required radius after t seconds, right? By taking 3 common, we have written here r equals to 970 plus 3 to the power 1 by 3, right? So this much is in this lecture series. Next we will see some more examples with respect to differential equation, that is nothing but our homogeneous equations. We will see in the next class. So till then, take care, stay at home, stay safe. Thank you.